Hello and welcome to a digital statistics lecture for Salt Lake Community College. In this video, we're going to be talking about section 9.2 for Math 1040, estimating a population mean. This is going to be a continuation of what we did in 9.1, where we talked about how to estimate a population proportion using a confidence interval. Here we're going to do the same thing, but the intervals that we create are going to be around population means instead. However, there's going to be an issue that we need to address with that. If we try to set up the same logic, we would still work with a point estimate plus or minus some margin of error. So that is still what we would set up. And we would do so by taking our point estimate, the sample mean, x bar, adding some amount of standard deviations times the standard deviation. This sigma over square root of n coming again from chapter 8, where we talked about how to find the standard deviation for a sampling proportion, or sampling distribution rather. The problem with that is right there, is sigma. How do I know what the population standard deviation is if I'm trying to estimate something about the population? If I already know the population standard deviation, then there should be no point of doing any of this. So we need to go into this with the assumption that I don't know anything about the population, which is most realistic. I usually am doing sampling in order to find something out about the population. If I already know the standard deviation, how it spreads, there should be no purpose to this. So what we need to do is a little bit of an alteration. In order to make it so we can use the sample standard deviation S, what we're also going to do is change this z-score into what we call a t-score instead. A t-score is going to be based on what we call the student's t distribution. That is what it's called. It even has it right here, student's t distribution. This is supposed to be something that was built in order to compensate for small sample sizes. Essentially, what had happened was the original creator, I think it was in the early 1900s for Guinness, the brewery, was hired in order to try to find how to work with just a small amount of barrels in order to run some statistics on barrels of alcohol. But because he couldn't really run a standard distribution or standard normal distribution because the sample size was so small, he had to adjust for that. And what we have here is student's t-distribution, which will allow us to adjust for small sample sizes and also allow us to work with sample standard deviations by essentially widening the interval a little bit more. That's going to all be based on the n-1 degrees of freedom, which we'll get into in just a moment. All right. Now, in order to work with all this, we still need to confirm that it is normal, which is what these three conditions are going to do for us. The first one we talked about last time, simple random sample. We still want that. Also, the sample size is small relative to the population, so n is less than 5% of capital N, or 5% of the population. So both of those are the same as they have been. The difference compared to 9.1, though, is that we're not going to look at NP1 minus P because we don't have a proportion. What we're going to do instead is check to see if the population is known to be normal or if the sample size is large enough, otherwise known as the central limit theorem. So that's coming back from chapter 8. Make sure you still know what that refers to. In terms of interpreting, we're going to interpret it very similarly. The interpretation here says with blank percent level of confidence, mu is between the lower bound and the upper bound, or that the parameter is between the values of the confidence interval. I will tend to shy towards the other interpretation that says with we are some percent level of confidence, so we are 90% confident that the interval contains the true, in this case, mean value. So always trying to relate the level of confidence to the interval that we create. Furthermore, all of these stay consistent as they did in 9.1. As you increase the level of confidence, the margin of error increases. As the sample size increases, the margin of error decreases. Those two are the same. However, the third one talks about standard deviation because we didn't really talk about standard deviation in 9.1. As standard deviation decreases, likewise the margin of error decreases. The reason for that is if you look at the formula here, standard deviation is on top. If I make that number smaller, that means I'm going to be multiplying by a smaller number, which inherently makes the margin of error smaller. This entire last three pieces being the entire margin of error. So if the standard deviation gets smaller, the margin of error gets smaller. Likewise, if the sample size gets bigger, the margin of error gets smaller. So make sure you just know how each of these values would interact. And if you're unsure, you can always plug in a value or change it to be higher or lower and see what happens overall to the interval. All right. One other last term is the term for robust. You sometimes see this. This is saying that things are accurate despite minor departures from normality. So even if it's not perfectly normal, it should still be relatively accurate, which is what we're going to be working with the t-distribution. The t-distribution is what we're going to call is robust. Now, the t-distribution itself, we've brought up because we had to talk about that to work with means. We had to talk about what the t-distribution was briefly in order to make confidence intervals for means. However, some actual properties about it. The distribution itself will look different depending on the degrees of freedom. The degrees of freedom is found by doing n minus 1 or your sample size minus 1. This should sound familiar from the original formula for a sample standard deviation, which had n minus 1 in it. I'll write it up here just so you can see what I'm talking about. The original formula for a sample standard deviation was the sum of your values, so your x sub I values, minus the sample mean squared, or the sum of your squared deviations, divided by little n minus 1. That right there was the degrees of freedom. It's also going to dictate how this distribution spreads more specifically. As you increase the degrees of freedom, what essentially happens is that this distribution should get closer and closer to what the standard normal distribution is, which is what the last note talks about. However, a couple things going into this. It's centered at 0 and symmetric about 0, which is the exact same thing as the z distribution, or the standard normal distribution. So it's centered at 0, it's symmetric about 0, so its value here in the middle is 0. The area under the curve is still 1, and the area to the curve to the right of the mean, or 0, is equal to the area to the left of that, which is also 0.5. This is still the same as z. As t gets bigger or smaller, it does get closer and closer, but never touches the horizontal axis, or y equals 0. Now, 2, 3, and 4, these are the exact same conditions that z has, or same properties that the z distribution has. 5, however, starts to go into how they differ. The area in the tails of the t-distribution is a little bit more than the area in the tails of the standard normal, and that's because the t-distribution is going to be more spread out, simply due to the fact that it's based on smaller and smaller, most likely, sample sizes, and if we have small sample sizes, we should probably make the distribution spread more. So it's going to be a little bit wider than the standard normal distribution. And as n gets bigger, the density curve gets closer and closer to the standard normal distribution. So as you increase your sample size, this curve itself should get closer and closer to what just z is itself. Okay. All right, so what we're going to talk about here is a couple examples of how to find the t-distribution using this table. You hopefully won't need to use it too much, but we can. You would first find the degrees of freedom, the row that you are in. So we're going to do that by going down this vertical column here. Then we're going to find alpha over 2, which if you recall is the area in the right tail. That's alpha over 2. Then when we find those two values, we pinpoint on the number we're looking for. So example, area to the right is 0.1 and the 28 degrees of freedom. All right, so 28 degrees of freedom means we're right here. Whoop. We're right there for 28. And then for area to the right, they already tell us is 0.1, so we're looking right here. So if we go down 0.1 and center on 28, we get this value right there, 1.313. That would be my t-score, which we'll use just like a z-score. All right. If the area to the left is 0.15 with only 8 degrees of freedom, which means our sample size was only 9, kind of small, then we center in on 8. Let me erase this other arrow here so I can draw it more accurately. Okay. So 8 is right there. Area to the left is 0.15. Okay, so because they're looking for area to the left, that means we're looking for, whoa, we're looking for basically a negative t-value here. So 0.15 is up here, and we center in on this value right there, 1.108. So we'll say t is negative 1.108. Because we'd be looking for the one that would be on the other side of the confidence interval. All right, now for a more typical problem, if n is 16, so what that means is that the sample size is 16, which furthermore means that the sample or the degrees of freedom is only 15. So right there, with degrees of freedom 15, 95% confidence, that means that there's 5% in the tails, or in each tail there's 2.5%. Scroll down with that, and we get 2.131. So the degrees of freedom would have been 15. Alpha is the area in the tails together, that's 5%. Alpha divided by 2 is 2.5%, and that leads us to 2.131. One more example of that for how to find the t-score if necessary. We will come back to this. If n is 33, and you have a 99% level of confidence. If n is 33, that means your degrees of freedom is 32. If you have a 99% level of confidence, that means you have 1% or 0.01 in the tails. And if you cut that in half to find how much is in each tail, you get 0.005. Then, looking at those two values, 32 being right there, 0.005 being right up here, we scroll down and we get 2.738. Okay. So that's the value I'd be looking for. Alright, so not too bad to use. Just find degrees of freedom, find the area that's supposed to be in the right tail, and you're done. Now for a couple examples of this. A Tootsie Pop is a sucker with a chocolate candy center. In a famous commercial, the question was asked, how many licks does it take to get to the center of a Tootsie Pop? In an attempt to answer this question, a survey of 92 volunteers were asked to count the number of licks required to reach the chocolate center. The mean number of licks was 356.1, with a standard deviation of 185.7. So that's my mean and standard deviation. That's x bar and s. If I interpret the 95% level of confidence for the number of licks required to reach the chocolate center. Okay, so to do that, what we have all our values in place, and we just need to run through and find our confidence interval. If you recall from 9.1, our confidence interval program was in stats and over in tests. The one that we used was one prop z int because we were doing one proportion z interval. However, we're not doing proportions this time. What we're doing is an interval that's based on the mean, and specifically it's based on the t statistic. So if you scroll down, if you see on number 8 says t interval. That's the one that we want. So if we run t interval, so over here I'll write down what we're typing in. So t interval. Remember, if you ever use any program in your class, always write down the inputs. So t interval, and then my inputs. In this case, the first thing asks us if we want data or stats. Data means that I have values in a list, which is what it's going to ask for. In this case, we don't have a list. So we're just going to put in the statistics, the raw statistics that we actually already have given to us. Firstly, it'll ask for x bar referring to the sample mean. The sample mean that we got was 356.1. The sample standard deviation we got, Sx, was 185.7. N, our sample size, they said that they had 92 volunteers, so that is our sample size, which means the degrees of freedom would be 91. The C level then is also given to us as 95%, so 0.95. Alright, so we just need to plug those in appropriately, so 356.1 followed by 185.7, 92, and 0.95. That gives us an interval that should be surrounding the mean of 356.1. We get an interval of 317.64 and 394.56. Alright, so that would be my confidence interval. Now for the interpretation, we have a little bit of a fill in the blank here, so I'll follow first what the blanks do, and then I'll talk about what I tend to prefer. There is in this case, we're looking at 95%. That's our level of confidence here. There's a 95% level of confidence that the population mean number of licks falls between 318 and 395 about. So 318 licks and 395 licks. So that's about where I expect to be for the average number of licks to get to the center of a Tootsie Pop. Now, again, that's how the interpretation is here, and again, that's how the textbook tends to do it. I recommend making sure that you try to think more about the percentage of confidence relating to the interval itself and not to the population mean. So say something more like, we are 95% confident that this interval up here, the one that we just calculated, so we are 95% confident that the interval contains the true population number of licks, or population mean number of licks. So relating the percentage of confidence to the interval that you created, and hoping that that interval contains what you're looking for. If you do this same thing with 99% level of confidence, that means that you're going to have this same t-interval stuff. The only difference is that C is going to change from 95 to 99. Now, before we do that, take a second and try to think about what the interval will look like if C changes from 95 to 99. Okay. If you thought about that, thought about thinking what would happen to that interval, we can do that here by going into stat, into tests, and running t-interval. The only value we should have to change is the C level itself to 0.99. And if we calculate that, what we should get is a wider interval. We get 305.16 followed by 407.04. Notice that is wider than the previous interval of 317 up to 390 or 318 up to 395. Ours now goes from 305 to 407. So we are more confident that this interval does contain the value we're looking for, but it's getting worse and worse because now I'm within 100 values, so I'm including even more numbers. I'd say there's a 99% confidence that the number of licks is between about 305 and 407. Or again, better way to analyze that is saying that we are 99% confident that this interval contains the true mean number of licks. Alright, so we have a couple more here So we have some on page 7 and 8. Again, I highly recommend now taking time and trying to see if you can work with at least the next few on your own. See if you can calculate those. How much time do Americans spend eating or drinking? Suppose for a random sample of 1,001 Americans, so random, that's good, we need to know that. 1,001 Americans, that's our sample size. Age 15 years or older, the mean amount of time spent eating or drinking per day is 1.22 hours, so that's my X bar, with a standard deviation of 0.06 or just 0.65. Construct and interpret a 90% confidence interval for the amount of time Americans age 15 or older spent eating or drinking. So those are all the values I'm looking for. First off, we can do random, or we can do normal, because we hit all the conditions. First, it is random. So it is a random distribution. It says so in the description. 2, if we look at what's going on here, we have 1,001 Americans, so 1,001 is likely less than 5% of all Americans. So 5% of the population, so that should be good. And thirdly, 1001 is also bigger than or equal to 30. So by the central limit theorem, we have enough. So everything is good for us to run t-interval. The conditions for means are a lot easier than they are for proportions, because you don't really have to do too much calculation. With t-interval, my first value, x bar, is going to be the mean provided of 1.22. My sample standard deviation is given to us is 0.65. The sample size is also given to us as 1001. And the sea level is given to us to be 90%, or 0.90. So we can plug that into t-interval here. Again, we have the statistics, so 1.22, 0.65, 1001, and 0.9. Plug all that in, and we get 1.11. I'll just do 2 decimal places because that's where they round the mean to as well. So I'll say 1.11 to 1.33. Just make sure, depending on the question, if it does ask you to round, you do so appropriately. So that gives us our distribution, or our confidence interval. Now, it also asks us to interpret this, so I'm again going to interpret it in what I believe is the correct way. I'd say we are 90% confident based on the level of confidence we're looking for, so we are 90% confident that I'll say the interval above contains the true mean, what we're looking for, number of hours spent drinking, the mean number of hours spent eating or drinking, which was the question. That'd be a great way to interpret that. And I can just reference the interval I just created instead of writing it down again. So a little bit easier. Okay. All right, one more page and we're done. The following data represents the age and weeks at which babies first crawl based on a survey of 12 mothers. So determine the point estimates for the population mean, and then construct and interpret a 90% confidence interval for the mean age at which a baby first crawls. So we have these values here. And what we're going to do is plug those into our calculator appropriately. So we have a list, should be able to plug those in. Now I'm going to take just a second real quick. I'm going to pause on my video and clear all this and put in those numbers. Okay, so I have all those values in. I also have the data for the next example in there as well. All right, so it asks us to find the point estimate for the population mean and then construct the interval on this. However, we could do all of that at one point. We would normally find the point estimate by just running OneVerstats on L1 and getting the mean. However, we can simply run t-interval on that list we made, and it will spit out both the interval and the point estimate for us. So that's what we're going to do. We're going to run t-interval on this. Real quick though, just to address the conditions. Both of these are going to be weak, and you may notice why already. The first one says the following data represents the age in weeks at which babies first crawled based on a survey of 12 mothers. So survey is basically all we have for randomness. So we're going to say assuming that it's random, and the other conditions are okay, then we should be fine. 12 mothers, that's our sample size. That's definitely less than 5% of all mothers, so that should be okay. However, 12 is not high enough for our sample size. It's not bigger than 30 in order to verify the central limit theorem. Now, that's not necessarily a problem as long as we know that the population is normally distributed. However, we do not know in this situation that the population is normally distributed. So, theoretically, the working with confidence intervals would not necessarily be appropriate here. We do not know that it's normally distributed. So there is definitely a weakness with this. Keep that in mind because sometimes we will be asked, is it even appropriate to work with this interval or is it good to do so? In this case, I would say no. We do not have enough information. But for the sake of an example, we will still work through it. With t-interval, in our calculator, we're going to go to stat. Once we have those lists set up, go to test and run t-interval. Now remember, t-interval gives you the first option of data or stats. In this case, we don't have statistics given to us, we have the data. So we're going to go over to data and hit enter on that. The screen should change, and now it asks us for a list. In this case, my list is the table here, my list of values. So my list is L1. That's where I put these 10 values, or 12 values rather. So maybe you put them in different lists, up to you. The frequency list, also we have 1, because in this case we don't have a paired frequency list. We don't have like 8 mothers had a value of 52 weeks, or whatever this is, yeah, 52 weeks. So another 10 mothers had 30 weeks. We don't have a paired frequency list, so we just put 1 to indicate each value represents a single individual. And then our C level we do have is 0.9. So all this is already set up for us. We run this, and we should get an interval that's centered around a mean. We get a mean, I'll say the mean first, because it did ask us to do that first anyway. So I'll say the mean is about 38.25. And we have a confidence interval that's centered around that. I'll say 33.07, so I'll round them all to 2 decimal places just for brevity. And then 43.44. All right, so it seems to be spreading by about a margin of error of 5-ish. Yeah. All right, so that would be that. It does also ask us to interpret it, so we are going to interpret that carefully. We're going to interpret this by saying here, we are 90% confident that the above interval does contain the true mean number, the true mean age, I'll just say, yeah, the true mean age, because that's what we're looking for, the age in weeks. Okay, so that's it. All right, if you want to put more into that, the true mean age at which babies first crawl. Yeah, so the true mean age of a baby's first crawl. That works fine as well. All right, so if we have the data, it's not too bad. Doesn't really change much at all. Just makes it so we don't have to do one of our stats separately because it's an easy enough process the calculator can do in the background. Another example of that, crash test results. The following data represents the repair cost for a low impact collision in a simple random sample of mini and micro mini vehicles. Determine a point estimate for the population mean and construct and interpret a 95% confidence interval for the population mean cost and repair. All right, another note on normality here. This one does say simple random sample straight up, so that's really good that it does say that explicitly, that we're dealing with a normal or a simple random sample. We don't always have that. However, even though we have that and we have, 10 vehicles, so that's probably less than 5% of all mini and micro mini vehicles, so that's probably okay. We still have the problem that our sample size isn't big enough, and also we don't know if the population is normal. By the central limit theorem, we would have to know one of those to claim normality. And unfortunately, we don't have them, so we cannot claim this is going to be perfectly normal. That means that our t interval that we calculate here is not necessarily going to be as appropriate as we would like. So it's going to be very weak. So just a word and note about that. In this case, our list here, I put my list in L2. I do not have a frequency list, so I'm going to keep it as 1. And my C level here, we're looking at 95%, so 0.95. So that's what we're going to do in my calculator over here. So we have the data. For our list, we're going to make sure that we put in L2. So second 2. Frequency list of 1, C level 0.95. And we calculate on that to get both our point estimate that we want and the interval surrounding that. So x bar equals 1,756.5, and that's in dollars. So I'll say 1,756.50. That's on average how much it costs to repair those. And then we have our interval that surrounds that of $1,035.80 on the low end. And then on the high end, we have $2,477.20. All right. Once more, it asks us to interpret it, so we will do so, and we'll interpret it appropriately. So we will say that in our percentage here, we are 95% confident that the above interval does contain the population mean cost of repair for mini and micro mini vehicles. All right, just putting the situation into context. And I'm just stealing a lot of the verbiage there directly from the situation itself. We're looking for mini and micro mini vehicles, so that's all I'm getting that from. All right, now a couple other things here. What would happen to the confidence interval if the confidence level increased? Well, if you increase the confidence interval, likewise the interval itself will increase or widen. So the interval will get wider. And what would happen to the confidence interval if the sample size increases? I'd have the exact opposite. The interval would get more narrow. I would have a lot more information, and therefore the interval will get a lot closer and closer together. Also, if I have more information, I may cross the threshold for CLT, so the confidence interval would actually be appropriate. But that's for a different case. All right, one last thing. Determining the sample size. We had a couple formulas for determining the sample size with the confidence interval for proportions. Now, if I'm talking about a mean, we have a little bit of a different formula. The formula is a little bit more, I'll say, condensed. So it's a lot smaller, or at least smaller looking. So we have here z sub alpha over 2, so that's going to be our z statistic, times s, our standard deviation, will give us our margin of error. Well, and divided by our margin of error squared will give us our sample size. So all of those pieces there. And we can determine the sample size using this. Now, notice that we are still using z sub alpha over 2. The reason that we're still using z sub alpha over 2 is because we are kind of assuming that it's getting closer and closer to a big sample. And what the t-distribution is supposed to do is, as the sample size gets bigger, it's supposed to get closer and closer to the standard normal distribution anyway. So we're still going to calculate that using inverse norm. You could do it with inverse t, but we're going to do this with inverse norm. With this situation here, and we're still just going to round this up. A recent Gallup poll asked Americans to disclose the number of books they read in the previous year. Initial survey indicates that's a sample size or sample standard deviation of 16.6. Estimate how many Americans need to be surveyed to be within 4 books. So that's my error. Those 4 books there, with a 95% level of confidence. All right. So we have the 4 books as our margin of error. We have the 95% level of confidence as well. So we can find this. We can solve for n appropriately. All right. So n equals the quantity. Z sub alpha over 2 we'll find in just a moment. We have our sample standard deviation, though, of 16.6. Divided by our margin of error of 4 books, quantity squared. To find z sub alpha over 2, what we're going to use is inverse norm, like we have done before. So we're going to go into second vars and run inverse norm. We want a 95% level of confidence here. So that means the area on the right side or the area on the left side is 0.025. That's how much area is there on in the tail. So 0.025 or 2.5%. Having troubles here. Okay. 0.025. Mean of 0, standard deviation of 1. And if I run that, I get 1.95996, or about 1.96. So I'll just say 1.96 to make my life a little bit easier. Times that. All right, now you could also get that using that table that we had shown earlier on section 9.1, because 95% is a very common one to look for. However, even if not, we can find it that way. Here we would have 1.96 times 16.6 divided by 4, parentheses squared. Now, I don't need to be too careful in terms of the division and multiplication on the inside there, because commutative and associative properties of multiplication and division are the exact same because it's the exact same function. So I don't really need to be too careful, but it's always good to just be careful with it. So go ahead and do like the multiplication first, find that, then divide it by 4, find that, and then square it. That works too. We get 66.16. So that means that we need, if we round that up, we need 67 books, or yeah, 67 Americans. Okay, so that's the sample size required for this. All right, that's everything for 9.2. I will say for my classes specifically, I have a program written that I highly, 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 highly recommend watching a video for. If you're in my classes, I have that linked in the calculator tutorials, and that will show you how to put those 3 functions to find the sample size in your calculator so that you can work through it kind of like the previous ones, kind of like just a program. And when you have all that done, you can just use that directly and don't need to worry too much about these formulas. But that's only if you're in my class. If you're in other classes, so if you're not in Mr. Woodward's class, make sure you do know how to work with the formulas like we did here. But with that said, I hope that helped. From here, go ahead and try 9.2 and also 9.3, because 9.3 is kind of just a review section through it. I will make a quick video for 9.3, but otherwise,